All right. So here we are at the final chapter of Rust, Atomics, and Logs. I'm going to have to use the mouse to advance. Okay. And here's our author last month at Eurorust. She was on a panel and called Inside Rust. And Luca Palmieri has just asked the panel what they would do if they had more time. And her answer was write another book. So the good news is she's willing to write another book, which is not nothing, because some people that write books have a terrible experience and never want to do it again. So good news is that's not the case with her. The bad news is it sounds like she doesn't have enough time right now, so we shouldn't look for one anytime soon. Chapter 10, Ideas and Inspiration, is different from all the other chapters. We did pretty much everything we're going to do in detail in chapters 1 through 9. Chapter 10 is just observing that there's a virtually infinite number of things we could do with a book of this title. And we're going to look briefly at half a dozen of these things and talk more about it. Each one of these things is a rabbit hole on its own, and you could go on and on and on with this for pretty much as long as you like. All right, so first up is semaphores. And they come from railway semaphores. So that's where they get their name. And they're effectively just a counter with two operations: the signal operation, also called up or V, and wait, which is also called down or P. More about that in a minute. So here's the illustration from the book showing that we can keep going up and we can't go down if we're at 0. And these go all the way back to this guy. Everyone recognize this guy? This is Dijkstra. And you probably know that name, if not that face, from his shortest path algorithm, or his structured programming essays, or the go-to statement considered harmful, or any number of reasons. But he's also came up with semaphores. And he kept very good notes throughout his life, and he called them EWDs, and he just numbered them. And semaphores are mentioned in EWD number 35. And relevant to this book, he kept very good notes, but apparently one thing he didn't do was write the date down. So we have to figure out the timing of this sort of with just happens before relationships. So like this paper references a paper in 1959. So we know that 1959 happens before EWD 35 and so on. So using things like that, they know that this paper was written in 62 or 63, but they're not sure exactly, which I found strange. And so he was writing in Dutch, but that's the Dutch word for semaphore. And the V and the P also come from Dutch. So that's why the weird names that if you spoke Dutch, they wouldn't seem so weird, I guess. And here's an excerpt from EWD 35. Now, this must be a transcription, I guess, because I understood that all the EWDs were handwritten longhand, but either this one was typed up or somebody else typed it up later. But here we see he's using the V and the P. And this is the plural of semaphore in Dutch. And he also is using a little bit of Hungarian notation here. He says the variable begins with S. So here's our SX variable. And the S is for semaphore. So it's not just the X variable, it's the semaphore X. And he's assigning it here and applying the V function here. And I think later in the paper, maybe even the very next paragraph, he says, after initializing it, you shouldn't assign it anymore. You should just access it with the V and the P. Oops, I wanted to go down. So in Rust, we could implement a semaphore with just a mutex for the counter and a condition variable for the wait. And then in chapter 8, we saw the futex, so we could do it that way and gain some efficiency. A special case of a semaphore is a binary semaphore, and that's just a maximum value of 1. So that's pretty basic, but we can build other things with it. So I've sort of adapted that illustration for that case. And we can initialize the counter to 1 and then wait for locking and signal for unlocking. That would give us a mutex. On the other hand, we can initialize the counter to 0 and then wait for park and signal for unpark, and that would give us signaling. So it seems to me that this is a better metaphor to the railway semaphores, because like this one on the left is down, and you can't put it down again, but you could put it up. When this semaphore on the right is up, and you can't put it up again, but you can put it down. So I was going to say that railway semaphores are really binary semaphores, not semaphores. But then it occurred to me that there are other types of semaphores that have more than 2 positions. Railway semaphores have, there are ones with at least 3 positions, if not more. So it's not quite right, but. And then I found this quite amusing, and this is in our book. We can make a mutex with a semaphore. We can make a semaphore with a mutex, but we probably shouldn't mix those too much. You know, sort of pick your primitive, right? And finally, we have further reading where we have a link to Wikipedia, as well as these Stanford course notes from 2008. So if you still want to read more about semaphores, those are a couple of links that will follow in the book. So that's semaphores. The next topic is RCU. And if we wanted to share data with multiple threads, of course, if we're not sharing data, we don't need this book at all. So these first 2 bullet points are sort of always there for this whole book, right? If we're sharing data with multiple threads, then in the case where we want to read a lot and only write a little, we could use a read-write lock. Or we could use atomic variables and avoid the locks. And that's fine if our data is like a single integer, but less fine if we have even 2 integers or something even bigger, like a whole struct of data. So we could solve that with another level of indirection, like every other problem in computer science, right? So our atomic then would be a pointer, and we can't modify the struct atomically, but we can replace the struct atomically, and that's almost as good. So RCU is read, copy, update. And here's the diagram from the book. And we have read, copy, modify, update, and deallocate down here shaded out. So if it's read, copy, modify, update, deallocate, we could almost pronounce that as ArcMud, but we don't. That's not what it's called. But let's go through that a little. So I've sort of deconstructed that diagram. So here's our struct and our pointer to it. And we can read from our struct and make a copy. And now we can modify our copy. And no one else knows about this yet, so we can take our time and do whatever we like. In fact, let's modify a couple of things just for illustration purposes. And now we do the update. So that's just the compare and swap operation. So we still might have people reading the old data, not through this pointer, but they followed it already, and now they're reading the old data. So we might have reader 1 and reader 2 still alive and reading. Reader 3 may be finished and left. Reader 4 is still reading. Reader 5 comes along and gets the new data. And it's perhaps worth pointing out that nobody has at any time, x equals 100 and y equal 456, or x equal 123 and y equal 400. They're either looking at the whole struct of old data or the whole struct of new data. And now the question is, when can we get rid of this? When can we deallocate the old data? And as the book points out, this is always the interesting part of RCU, even though there's no D in RCU. This is the interesting part, not the read, copy, update part. And here it is in words. We can't get rid of the old data until everybody's done reading it. So what can we do? Well, there's a number of things we can do. The first is we can just ignore it. And this sounds facetious, like maybe we might be joking, but this is a valid solution for some use cases, right? You might have a short-lived program or some other reason, or remember back we started talking about RCU in terms of reading a lot and writing rarely, updating rarely. So if we're only doing a few updates and the updates are small relative to the rest of the data in the program, maybe the leaking memory isn't really that big a deal. And just recently, the IRA project was totally unrelated to RCU. This is a totally different context, but they just recently, I happened to come across this, and I say, "Oh, that's interesting." It's sort of a different version of the same case. They dealt with unsoundness of environment variables by choosing to leak memory instead. So that was a sort of workaround, if not solution, to an unsoundness issue. And their basic observation is that leaking is not unsafe. And this reminds me of in Rust, panic is not unsafe. People talk about panicking and like it's evil to have unwraps in your program or whatever, and it's kind of not. It's like panic is not an unsafe operation. Well, leaking isn't either. So, on the other hand, also at Eurorust last month, we saw how horribly complicated memory leaks can be. So maybe you don't want to deal with that. This was a really good talk. Yeah, so what else can we do? So the usual thing you might think of in this situation is reference counting. If you have some, if everybody sort of keeps track of increments the counter whenever they're going to read something, and if the counter's at 0, nobody's reading it anymore, and we can get rid of it, deallocate it. Another alternative is garbage collection. So if we were doing this in something like Java, then we could just do nothing, and eventually the JVM would notice that nobody's using this data and collect it for us. So the Rust runtime famously has no garbage collector, but we could write one, and we wouldn't necessarily even have to write a general purpose garbage collector. We could just write one that collects our particular data structure for our garbage. And then there's something called hazard pointers, and this is sort of like the reference counting inverse of it. Or every reader would sort of keep a list of the data it wants, and then the writer would have to check with all the hazard pointers to make sure they're empty before deallocating. And then quiescent state tracking. My, that sounds fancy. So in all of this locking business, the whole general topic that we're talking about, we're always concerned with the critical section of our code. And did we acquire the lock for the critical section? And is the critical section over and we can release the lock and things like that. So quiescent state is just not the critical section. So it's perhaps not as fancy as it sounds, but And RCU was used in the Linux kernel starting in 2002. Actually, before that, if you're the type that compiles your own kernel, you could have optionally compiled RCU in the 2.4 kernel, and maybe you did that. But RCU existed before that. This wasn't the first occurrence of RCU. This is just when it occurred in Linux. And I think that's where this abbreviation RCU came from. In fact, that might be the only real contribution from the Linux kernel is the abbreviation RCU. Although they've also sort of inadvertently, I think, gifted us these comments, because ever since most of the references I encountered after 2002 say RCU is a read copy update with 2 commas like this, and the ones older than 2002, you see read copy update with 1 hyphen like this. And this is subtly different, maybe not so subtle. This is like the single adjective read copy modifying the update. Like, we're ready to do an update. What kind of update are we going to do? We're going to do a read copy update. So this seems to make more sense to me. But neither name is really very good, so maybe it's silly to be pedantic about it. In fact, it might even be best to just forget about the words and just call it RCU. And this is the opposite of my usual opinion. If you've been in these online meetings with me before, I'm that guy in the chat expanding initialisms and acronyms that people use without explaining them. But here I'm advocating for the reverse. And it's like, let's not expand it at all. We just start calling it RCU. But I guess as Rust programmers, we are sort of used to that already. The Rust compiler is a multi-stage compiler. In the last stage, we just hand off to LLVM. And if you've ever thought about what LLVM stands for, I mean, you can go look it up, but it's not helpful. It's not going to help your understanding. You might as well just think of it as LLVM standing for LLVM and not worry about what it stands for. Well, I propose maybe RCU is the same way. So one of the things I did investigating, looking into learning more for this talk, was watch this conference talk from the C++ conference a few years back. And it was really good. I learned a lot. But in particular, I borrowed one of this guy's slides. He had a really excellent slide on when to use RCU. And there's sort of 2 axes here. The updates being rare, and remember that was sort of a precondition for when we started this RCU section. We're going to write rarely and read a lot. So the updates are rare. And the more frequently we need to update, the less attractive RCU starts to be. But then there's this other axis with the consistency. So this is the notion that we're okay with having those old readers still existing, right? Perfect consistency would mean as soon as we're done with the update, we insist that everyone has the new values, like the 1, 2, 3, 4, 5, 6. Perfect consistency means nobody still has 100, 400. Everybody has the 1, 2, 3, 4, 5, 6. So if that's the case, again, RCU is not attractive if you really require consistency. But if you're okay, then that's why this upper left-hand corner is RCU heaven, right? This is what it's made for. But like in 2002, they've added like one thing to the Linux kernel here. And in the meantime, the last 20 years or whatever, they've been RCUifying more and more stuff. I think they're sort of moving down and to the right as they go. They're doing more of these green things and maybe even getting into the chartreuse area now with all the RCU stuff. So in addition to read copy update, it's sometimes called passive serialization, MP defer. And the one I think I like the best is generations. In our example, we had just 2 generations, the new data and the old data. But you can imagine if we came along with another update, we would have new data, the old new data, and then the old data. So there would be 3 generations, and you could even have more than that. And you can imagine sort of naming these things by generation and keeping track of these things for the purpose of reclamation by generation. So too bad that name didn't catch on. I think that's a better name than RCU. And as just in another illustration that none of this is new, let's see if we can. Passive serialization was patented. They applied for the patent, the U.S. patent, in 1986. It was granted in 1989. So there's that. So that's 30-something years old. MP defer, that's an IBM thing, and I guess that didn't age well. They probably just want to call it MP defer now, but that's a whole category of things at the IBM VM world. And then I looked for crates on Crates.io that talk about RCU. This ArcSwap any crate has an actual method called RCU, and the sort of beginning description is a pretty good elevator pitch for what RCU is. If you need to tell somebody what RCU is in 5 sentences or less, then this is not a bad way to go. You could do worse. So hooray for documentation. And then there's a couple of crates that actually have RCU in their name. And then the crossbeam crate, or family of crates, that's the data parallelism stuff. They call it Epoch, which this is a group. I like that name. That's similar to the generations name or whatever. An epoch is like a generation. And then further reading, we have the Wikipedia link, and you'll notice, or I noticed at least, that Wikipedia didn't go with the 2 commas or the 1 hyphen, but with 2 hyphens. So thanks for clearing that up, Wikipedia. And then this link is to Linux Weekly News in 2007. So that's 5 years after RCU was added to the kernel. And in those 5 years, they had sort of RCUified a few more things. So people, I guess, were starting to notice. And they wrote there's a whole family of articles on. Let's look at that, because, yeah, this guy, this is written by 2 people. The first of which, his name comes up all the time, going back way before 2002. So I think he's deep into this RCU business. And then I came across this paper, comparative performance of memory reclamation strategies for lock-free and concurrently readable data structures, which I guess is this guy's master's thesis at university. But I liked it for a number of reasons, but one is it's another example of this hyphen stuff, because there's 3 kinds of reclamation here, and the hyphenated quiescent state-based reclamation and the hyphenated epoch-based reclamation, and then sadly safe memory doesn't get a hyphen, so English is hard, I guess. But it's interesting. The QSBR is normally associated with RCU type stuff, and these other 2 are different kinds of lock-free stuff. And in this paper, he demonstrates that you could actually use this with the lock-free things, and or these other 2 could be used in an RCU situation. So they're all sort of interchangeable in that sense. All right, that was RCU. So next up is lock-free linked list. So if you're sick of RCU, I've got bad news for you, because this is more RCU. So if you want to make a lock-free linked list, one way you could do that is with an atomic pointer and point to the next one, and that's a linked list, almost by definition. So here's the diagram from the book. Showing creating an update. So, or an insert, I guess. If we want to do an insert, we allocate the new element, pointer to the first element, and atomically update the initial pointer to us instead of what it was. So here's a different diagram showing that, where here's our new guy, and then the last thing we do is update the head to point to us instead of the old head. And then a delete is atomically update the pointer to the element after it. So that's this situation. That's a little bit easier. But there's more to it than that. If you want to have multiple writers, now again, this is we're hoping writing would be rare, but if you want to support concurrent insertion or concurrent removal, there's more work we have to do to make sure we don't screw that up. We might remove something that has just been inserted and or just been deleted, and we'll sort of resurrect it from the dead and so forth. So it might not be worth it. You might use a regular mutex to avoid multiple writers, and then reading is still lock-free. So that sounds attractive to me. But again, as we said, I think more than once now, the interesting part of RCU is reclaiming this deallocating. So we have the same situation here. If we want to delete items from the list, when can we get rid of them? There might still be people reading them. So, but all those same solutions that we talked about in the RCU section apply here as well. And more generally, there's all kinds of things we can do with compared swap and lock-free data structures and so forth with atomic pointers. But whatever we do, we're going to need some strategy. As part of our program is going to have include a strategy for deallocating or somehow reclaiming ownership of the allocations. So further reading for this section is, again, Wikipedia, and then Linux Weekly News again, how to use RC for linked list case studies. Next up, queue-based locks. So this is something we usually think of as the operating system doing, but we could do it ourselves in user space, or maybe we're writing an operating system. But we could implement a mutex by manually keeping track of the queue of waiting threads, and then we need some sort of atomic pointer to the list of waiting threads. So we need sort of one of these standard threads to be able to wake it up. And then we could use unused bits of the atomic pointer to store the state of the mutex itself. So that looks like this. So here's our atomic pointer pointing to the queue. So here's the thread object, if you will, and then all the way down to the end. And apparently there's a lot of different ways to do this. The queue could be protected by its own lock bit, or we could use a lock-free or partially lock-free data structure. We don't have to put things on the heap. We could use local variables in the thread. Um, we could have a doubly linked list with pointers to the previous element as well as the next. And we could also point from the first element to the last element, and that would give us an efficient append. And then if we only block and wake up, then this could be used to build something like thread parking. And this is how Tim J talked about slim reader writer locks in Windows back in chapter 8. And that's a queue-based lock. So further reading on that is this is I think this is a RFC that Mara wrote. So she's referring to herself there. And the Rust implementation of queue-based locks is called usync. So it provides all of these types. So you could use usync mutex instead of standard sync mutex or all these other guys. And related to that is parking lot based locks. So if we have a very small mutex and if we move that queue into a global data structure, then we only need 1 or 2 bits inside the mutex itself. So we could get away with a single byte for the mutex. And I thought this is starting to get a little too fancy for me here if we're going to start using unused bits in a pointer or whatever. So I'm starting to feel uncomfortable with this solution. But then earlier this week, I came across in a totally different context a blog post talking about storing data in pointers. Although it was a bit of a cautionary tale, so maybe I was right to be a little afraid of this technique or whatever. Because like if you're used to AMD 64 architectures or whatever, you have 64-bit pointers, right? But you only have 48-bit addressable virtual memory. So 16 bits for free, right? You can use those. Well, this blog post is about these similar and related architectures that use more than 48 bits, including, I think there was one that was 57 bits. So that's bigger than 56 even. So there's not even a whole byte left over. So store data in your pointers at your own risk. So back to parking lots. We could use a hash map and map memory addresses to the queue of threads. And this is what's called a parking lot. So it's a collection of parked threads, right? So here's what that looks like. We have our single byte or whatever, if we're going to steal bits from somewhere else, maybe. And then a reference to that, it points to our hash map, which is our parking lot. And then our queue of threads is over there. And we can generalize this to track other things and get futex-like functionality out of that. So famously, WebKit did just this. So this is the WebKit solution for locking its objects, which is, of course, the JavaScript web GUI building thing. And then Rust has a parking lot crate, which is similar, or works similarly, I should say. And both are mentioned in the further reading references. And similar to the earlier usync and whatnot, parking lot provides alternatives for these things. You can use parking lot mutex instead of standard sync mutex and so forth. And sequence lock. think this is the last one. So this is another way of updating larger data without traditional locks. And this is really cool. I'd never heard of this, and I think it's just neat. So you have an atomic counter that's odd while the data is being updated and even when the data is ready to be read. So the writing thread increments it before and after it writes, and reading thread will read it twice. And they can do that without blocking, right? The reader can just do this. They might have to retry, but they don't have to stop anybody or acquire anything. They just do it. So here's the sort of summary diagram, and this is just beautiful. I just love this. I never would have thought of this, but now that I've looked at it, it's like it's just beautiful. So I sort of want to do things this way now for other situations. And apparently this is an operating system kernel thing, which is maybe explains why I haven't used it. I've not written an operating system kernel. But, excuse me, that's my phone ringing. So one possible technicality with all of this is how does this fit in with your memory model? Technically, you should be doing atomic operations, reading and writing this data, even though the whole thing doesn't have to be atomic. So it's maybe not as simple as it looks. But so the references for further study here are you can look up seeklock on Wikipedia. Is this another Mara? Yes. So this is her own RFC. And then the seeklock crate, which I'm going to look at a little bit more now. So here's this text is pulled from the documentation for the crate. So it gives you a seeklock type, and it's claimed to be faster than the standard library read-write lock. It only works for copy types, so that's a potential downside. So if you need to use read-write lock for something that isn't copy, then you'll have to go back to the standard library. And this is the synopsis for the seeklock crate, and I included this just because I'm almost at the end now, and I haven't had any Rust code in my talk yet, so I wanted to put something in here. So here's the how to use the seeklock crate. Oh yes, and then there's one final section where now that we're all experts in Rust concurrency, we're urged to go out and write blog posts and give conference talks and all these other things to share our expertise. Because apparently there's not enough of these things out in the world already, and we need more. And this is kind of difficult, challenging stuff for a lot of people, and maybe so much so that they are afraid to write about it. But maybe we should be less afraid and start writing more, talking more. That's all I had. So
awesome. Thanks, Tim.
Yeah, thanks for the opportunity of doing this. I learned a lot just preparing this, so I was happy to do it.
You did a cracking job. Do we have any questions or any thoughts on the chapter or just the book in general. This is also a reflection time for, we finished the book. We've gone through it all. How are people feeling about it? You can type in the chat if you don't want to speak out loud. Stunned silence is also totally valid. Feeling post this book.
Yeah, thank you very much. So I love the talk a lot, and I have the feeling like there's so much more to see. Like there were so many references, and I also enjoyed this later data structures a lot, where we had like this queue-based and sequence log. It was quite interesting to see. So I think maybe now we can become confident to write or talk about this, but it's always hard, hard material, right?
That's right. This is really sticky stuff.
And I think one of the nice things about like doing a book club and then also like putting content out is, if someone watches a video and notices a mistake, hopefully they'll put it in the comments. And, we're none of us pitching ourselves as as being like world leading experts in concurrency, but we're interested and we're trying to learn it. And the more people like put stuff out there and get corrected and correct each other, and hopefully the like better collective knowledge of this stuff will become, because there's definitely a gap. Like that's why this book was so amazing, because there just isn't one similar that I know of that exists that tries to make atomics and locks and concurrency proper primitives accessible to
Right.
Yeah, it's really very, very helpful to have somebody like lay out this stuff with this. There are a lot of great diagrams in there, and it's really quite concise in explaining, so it's not too long to read, but on the same page you have so much, it's easy to picture that, so it helped a lot. So
like the book's slim enough that you just feel like I have to finish it. Like I can finish a book that's this thin. I must be able to, despite the density. And I feel like that was maybe partly deliberate. And it's not like there's not tiny fonts, like you say, there's still diagrams. It doesn't feel like it's excessively small, but it's just the nature of the topic means you just have to think about it. Like you can say it in not that many words, but it takes a while to like take on those words and actually absorb them properly.
So I'm still curious, Tim, do you have like a background like with a Linux kernel? You seem to like your references, they were really well researched also with all the papers of Dijkstraat and so on. So it was
No, I've been using Linux for 30 something years now, but I don't have any. I didn't contribute to the Linux kernel or anything. So
yeah, my time in Linux is like so long ago, and I was a fan of this. Maybe you know it, Gentoo distribution. So around 2006.
okay,
So you could like everything got compiled from the package manager, and you could change the C flags. So what kind of optimizations are used? That was quite cool. A long time ago. Nowadays, I'm just a Windows user.
so you get slim reader writer locks instead.
Yeah, that's true. And it was like it was queue-based blocks, right? Yes. Right. Yeah, very cool.
Wish I fully understood how I mean I haven't made any efforts to, but like how WSL behaves like with respect to these things, like presumably some kind of conversion between them like this.
So, as I understand it, it used to. I think WSL1, which they're calling it now, now that we have a WSL2, WSL1 was sort of mapping from Unix system calls to Windows, whatever they call them in Windows. Whereas WSL2, they gave up on that strategy and they just basically import a whole Linux kernel. but
I,
they sort of
yeah,
did try for a while. Yeah.
I think it works quite good as long as if you don't have like some there can be some mistakes made with the file system because it's very you can have a shared file system, but that is quite slow on the WSL side.
Just picking up on something you said earlier, Tim, about acronyms. WSL, Windows Subsystem for Linux.
Yeah, that's true.
So many.
There's so many acronyms.
So in terms of book clubs going forwards, me and Tim H, Oil and Sheep, actually I'll just refer to you as Oil and Sheep Golfer. And
Either one is fine.
We're saying maybe, so if people want to like post suggestions in the Discord, I'll post like a leader comment saying, please, yeah, put forward your book suggestions, and then maybe we can do like a poll over the Christmas break. People can vote on what book they might want. If people, people might vote and say we don't want another book club. I personally really like the book clubs. As it kind of I think it encourages us to keep a cadence up with the meetup that's tricky to maintain with just sourcing new speakers every time with no like signal. Oh, something interesting about types is one of the suggestions. All right, I'll have a look around. And it doesn't have to be, I guess it doesn't have to be like a physical book. It could be an online book. It could be just like a series of tutorials that people want to go through.